So we have a group of charges, Q1, Q2, whatever number of charges you have, Q4, and we're interested in finding out how much energy if I bring a test particle in the neighborhood of these charges. Let me call these charges test charges. The source. These are I'm going to call them the source. I'm interested in bringing some test charge over here and seeing what's the energy that it will take me to bring that test particle to some location in space. So I'm going to put an axis here and say that I'm bringing that test charge to some location in space described by the vector r. Okay? So the approach was to look at the electric potential energy of this whole setup of the source charges and the test charge together, right? So we said that if we looked at that potential energy, we would end up with the sum over all the different pairs that you have in your problem, right? It's K, Qi, Qj over the distance between all of the different pairs. So that's Rij. And we can break that sum into two terms. One term which has to do with the sum over all of the pairs inside the source. So the sum of all those pairs, I'm going to call it U source. And the rest of the terms are the terms that have in them the Q test, the test charge that I brought, right? Because one of these Q's in this term, for example, here, will be the Q test. In some of the terms, that will be Q test with 1, Q test with Q2, Q test with Q3, and so on. So I'm going to pull out all of those terms that have Q test. I'm going to write Q test explicitly outside, factor it out of that, and then what the rest of it, the sum, is over all of the charges of the source and the term K, Q, call it J, divided by R, and the distance is between the source charge J and the test charge that I brought to the problem. And this is the potential energy, which depends on where I place my test charge. Right? It depends on R. So then this term, the second term, is the one that I'm interested in, because that's the term that is going to change depending on whether I bring a test charge or not, where I place the test charge. The other term, the U source, is a constant term. Sources are, the way we think about sources is that those are charges that are somewhere in space and we don't mess with them. We put them somewhere and that's the way they stay, and we just bring other things around, right, and see what happens. So the source is going to be some constant number, the potential energy of the source. It's going to be some constant number, but the one inside the red circle, that's the one that I'm interested in. So that one, I can write it in a different way. Just from that, I can write this, that the potential energy of the sources, of the interaction between the source charges and the test charge, that's the term that I have inside the red circle, and that's Q times the sum over all the source charges, K, Qj, sum over J, of Rj, comma, test. This is the charge of the test particle. That term, the summation, we have a special name for that term. We call it electric potential. It's going to be a function of R, and it's simply the sum over all the source charges of the terms K, Q, the index there is going to be J, Qj over the distance between the vector R and the vector that describes the location of that charge, the source charge J. Okay, so the distance that I'm talking about there, of course, are this. This is R, say 5 comma test, right? Which is the difference between the vector that describes the location of charge number 5 minus the vector that describes the point in space where you put your test charge. Okay? So this vector over here is R5 minus R test. Right? So that's the idea with the electric potential quantity. Notice that that quantity depends on space, so at every point in space I'm assigning a value of that quantity. It's a scalar, right? It's just a number, kq divided by some distance. That's a number, it's not a vector. So that has the same kind of characteristic of electric field. For electric field, we say we have some charges in space, right? And we're not going to move those charges, and we're interested in finding what's the force on a test charge that I bring in the proximity of those source charges, right? So what we said was we're going to calculate the electric field due to the source charges at many different points in space, right? And that's what we call the electric field. And if we're interested in the force on a test charge, we just take the electric field at that location and multiply by the test charge. That's the same idea that we're going to use here, where space acquires a new property, potential, electric potential property, when there are charges in that space. Just like space acquires a new property, electric field, when there are charges in that field. So notice that that quantity, if you were interested, so this is the source, these are the source charges here, and you bring some test charge over here, and you bring that test charge from infinity to a distance, to some location in space, right? The amount of work necessary to bring that test charge from infinity to that location, notice that that amount of work is described by the potential, electric potential that we just described, that we just found out, right? Because the amount of potential energy that you, the amount of work that you have to do to bring that charge to that location is equal to the increment in the potential energy of the system, right? So remember, as we just wrote in the last page, that the total potential energy of the system is given by the term that has to do with the potential energy of the sources plus the potential energy of the sources interacting with the test charge, right? So when I bring a test charge, that's the term that I add to the total potential energy of the system. Because if the test charge was 0, if I don't bring anything, then I don't have that term in my summation, right? So the work done to bring that test particle from infinity to bring it to a location R in space is exactly equal to the increment in the potential energy of the whole system, and that is just simply Q test multiplied by the potential at that location in space. And this potential, again, is due to the source charges. It has nothing to do with the test charge. It's only due to the source charges. Those are the ones that modify the space around, the space where you're bringing your test charge.